Hi everyone, welcome back to Tech-Bimba channel. In the previous video, we discussed about a thread lifecycle. In today's video, we will dive into monitor lock and a synchronization in Java. Before we talk about monitor lock, it is important to understand what goes wrong when multiple threads share the same resource. If they do, we encounter the issues like data inconsistency, race condition, and unexpected output. Let's see this with an example. We have a class with a name counter with instance variable count set to 0. Within the increment method, we are doing a count plus plus. This count plus plus is not atomic operation. Internally, it uses a 3 steps. First, old value of count will be read from the memory. Then value of the count will be incremented to 1. Finally, the updated value will be returned back to memory. Next, we have a class with a name shared resource test. This class has a main method within which we are creating the instance of a counter. Then we are having a thread T1 and a T2. Thread T1 runs the for loop. Within each iteration, we are calling the counter method. That is, we are calling the increment method on top of a counter. Thread T2 also does the same thing. This is how thread T1 and a thread T2 are sharing the resource counter. Then we are calling the start method on T1 and a T2. At the line number 27, we are printing the value of a count. If you notice here, counter.increment method is called totally 20,000 times. So thread T1 calls this method 10,000 times. Thread T2 also calls this method 10,000 times. So totally 20,000 times this method has been called. Inside the increment method, we are doing the count plus plus, because of which expected output is 20,000. Now let's run this one and see what output we are going to get. If you run this program, we are getting the output as a 0. Now let's try to understand why we are getting the output as a 0. Once we do t1.start and a t2.start, at this point there will be 3 threads. One main thread that is actually executing the main method itself. Now thread T1 will ready to execute this lambda expression. Thread T2 will ready to execute this lambda expression. It's up to CPU scheduler. CPU scheduler might give a CPU cycle to T1 or T2, or it might continue with the main thread since it's already executing a main method. In our case, main thread got a CPU cycle, means it continued. Since it's already having a CPU cycle, it continued and it finishes its execution even before T1 and T2 started their execution, because of which we are getting the output as a 0 here. To fix this, we somehow need to make main thread to wait until T1 and T2 has to finish their execution. For that, there is a method called as the join method. If you call join method on top of a T1, we are saying main thread to wait until T1 finishes its execution. If you call the T2 T2.join, now main thread will wait until T2 finishes its execution. Now if you run this program, we are getting the output as a 17,610. Still we are not getting the expected output, which is 20,000. Now let's try to understand what is happening and why we are not getting the expected output. With a T1.join and a T2.join, now main thread will wait until T1 and T2 finishes its execution. So either T1 will get a CPU cycle or a T2 will get a CPU cycle. Let's say T1 got a CPU cycle. T1 entered into increment method. So it will read the old value of the count, which is 0. Count will be incremented by 1. Now thread T2 got a CPU cycle. Let's say it got a CPU cycle because of a context switch. Thread T2 will enter into the increment method. Since whatever the updated value of a count is not yet returned to the main memory by T1, it will read the old value, that is 0, from the memory, and it will modify the value of a count. So now count will become 1. That 1 will be returned to memory. If you notice here, thread T2 missed the updated value of a count, because of which we are not getting the expected output 20,000. So this is one drive. So same thing will happen whenever the This loop runs and every time context switching will happen, thread T1 and T2 are missing the updated value of a count, because of which we are not getting the expected output, which is 20,000. If you run the same program again, we are getting the different output. So every time we are getting the different output. So reason is for each run it's up to CPU scheduler. Sometimes thread T1 might be getting the CPU cycle first, sometimes thread T2 might be getting the CPU cycle. So even duration of the CPU cycle varies for each run, because of which we are getting a different output for each run. And also if you notice here, thread T1 and T2 are racing with each other to change the value of a count, because of which we are facing a data inconsistency and unexpected output. This is the statement we have seen at the start of the video, right? If multiple threads share the same data, we will end up with the issues like a data inconsistency, race condition, and unexpected output. Now, solution to this problem is a monitor lock. When we create the object, JVM maintains a object's metadata. Within the object's header, there is a lock called as a monitor lock. This lock is associated per object. JVM also maintains the data like whether this monitor lock is free or it is acquired by any thread. In case this monitor lock is acquired by any thread, so none of the thread will be able to acquire that until it is released by the already acquired thread. So to leverage the monitor lock here, in our case, we have to make this method as a synchronized, or we have to use the synchronized blocks. Let's first see synchronized method. If you make this method as a synchronized with a keyword synchronized, now first let's run this one and see what output we are going to get. Now we can see that irrespective of how many times we are going to run, we are getting the output as a 20,000. So what is happening here is, once we do T1 dot start and a T2 dot start, let's say T1 got a CPU cycle, T1 will come here and it will check whether the monitor lock on this is free or not. Let's say in this case it is free, so it will enter into the increment method. The old value of count will be read from the memory. The value of count will be modified, so value of a count will be 1 now. Now before writing this updated value to the memory, let's say T2 got a CPU cycle. So thread T2 will come here and it will check monitor lock on this object. Now monitor lock is acquired by thread T1, because of which thread T2 won't be able to enter into this method. So it will enter into blocked state. Once thread T1 wakes up, and it will perform the operation like wherever it left out, right? So it has already updated the value of a count to 1, so that will be returned to a memory. Then once it releases the monitor lock, thread T2 goes to runnable state. It will acquire the monitor lock on this object and it will enter into the increment method. Then it will read the value from the memory. Now it will get the updated value of the account, which is 1 now. So it will modify the value of account. So value of account will be modified to 1. Then it will be returned to the memory. So the synchronized ensures that at any point of a time, only one thread will be able to enter into this increment method, because of which now we are not missing the updated value of a count, and because of this reason only we are getting the expected output, that is 20,000. Since we are already having a synchronized methods, and these are actually solving the issues in case multiple threads share the same resource, then why there is a requirement of a synchronized block is the next follow-up question. If you notice here, in case of a synchronized method, we are locking the entire method. But it is not required that entire method itself is having a critical section of the code. This method might be having a critical section of the code as well as a non-critical section of the code. What I mean by critical section of the code is it have an impact if multiple thread access that code. Non-critical section of the code is that part of the code it does not have any impact and it will not lead to any issues if multiple threads access that line of a code. So in case of a synchronized block, what we will do is we will segregate what is a critical section of the code and what is a non-critical section of the code, and we will enclose the critical section within the synchronized block like this. With this, instead of blocking the entire method, we are enclosing only the critical section within the synchronized block. With this, performance will be increasing, and also it will give the more flexibility. If you notice here, synchronized method always obtain the lock on the this object, whereas in case of a synchronized block, we can specify on which object we want to acquire the lock. Let's say we want to acquire the lock on this object, right? Object lock equal to new object. This one is the what we have created. Now if you want to acquire the lock on this one, we can specify that object like this, and then we can specify the critical section. So considering the flexibility and the performance, it is always better to use the synchronized blocks. So now if you run this example, so it's the main class. Here we are having the same code whatever we are having in a shared resource test. Now if you run this program, we will get the same output. So we are getting the output as a 20,000. Now last concept in this video is we can use the synchronized keyword even with the static methods. In this example, we can see that there is a class with a name test. We are having a method m1 which is a static, and we are having a synchronized keyword with this m1 method. So this m1 is a static synchronized method. At the line number 7, we are printing the name of the thread, and we are appending with a text entered m1. At the line number 10, we are having a thread.sleep. So we are passing the parameter as a 2000, means the currently running thread will go to timed waiting state till 2 seconds. This sleep method won't list the monitor log that is acquired by the thread. At the line number 14, we are printing the name of the thread, and we are appending it with a text exiting m1. So this demo class is the one having the main method. Then we are having a thread t1 and a thread t2. Thread T1 is calling test.m1, thread T2 also calling test.m1. Then we are calling T1.start, T2.start. So now if you execute this program, we can see that thread 1 got the CPU cycle. Okay. So because of which we are able to see that thread 1 entered M1. So it's the name of the thread. So we are seeing the output as a thread 1 entered M1. Now line number 10 will execute. So this thread will go to sleep state. Now the state of the thread 1 is a timed waiting state. This sleep won't release the monitor lock, right? Because of which, even though context switching will happen, even though thread 2 got the CPU cycle, it is not able to enter into this M1 method. It will be into the block state. Only once thread 1 execute this line and releases the monitor lock, then only thread T2 will be able to acquire the lock, and it will able to enter into this method. That is the reason once thread 1 is exiting from the method, we are seeing this line thread 2 entered into M1, then thread 2 is exiting from the M1. This is how synchronized static method acquires the lock at the class level, and ensuring that at any point of a time only one thread will be able to enter into this method. So that's it about the monitor lock and synchronization in Java. In a next video, we will dive into inter-thread communication. If you found this video is helpful, please like, share and subscribe to the channel. See you in the next video. Thanks for watching.